D11, Kepler's third law constant. Now we derived Kepler's third law from first principles, while Kepler came up with this law empirically from data, and that's the cube of the distance from the sun to the planet, measured from center to center, is equal to some constant times the period of the planet, the time it takes to go around the sun. Kepler found that planets go in orbits that are ellipses rather than perfect circles. So with an ellipse, you have here a semi-major axis. The major axis for the ellipse is this long one. And then the minor axis is the shorter one. This is semi-minor. And it's this value here, the semi-major axis, that is your R. Now, since the planets have very little ovalness to them, we say the eccentricity is small. That means it's close to a circle. In my treatment, we're going to just consider the planets to be going in circles around the sun. But just bear in mind that R technically is the semi-major axis. So to understand this, I went to Windows to the Universe, which is a website developed by the National Earth Science Teachers Association based in the United States. And they have good data, but the data is easy to find. Planetary data, solar system data, easy to find. So here we're going to look at 3 planets. We're going to look at the Earth, and we're going to look at the distance from the sun in astronomical units. That's the unit which is the meter stick of the solar system. It's the distance from the center of the sun to the center of the Earth. Actually, technically, it's going to be the semi-major axis, but we're going to just consider a circular path. So we can just simply say it's the radius. And then we'll look at the period in years. And then we'll look at the constant, which is r cubed over t squared. That's the constant from this equation here. K is r cubed over t squared. And the units are astronomical units cubed over years squared. Now, in these units, things are very, very simple for the Earth because we have 1.000. We'll use 4 significant figures here. But by definition, that's going to be a 1. And then the year, or the planet's time to go around the sun, is 1 year. That's the time for the Earth to go around the sun. So this is 1.000. And if you cube the 1 and square the 1, you get 1 over 1. So this is going to be 1.0. I'm going to use 3 significant figures for this because I'm going to be looking up data for some other planets. And that's going to be Earth. Now let's look at Jupiter. Jupiter has a distance r. It's going to be 5.2028. I like to keep more places and then round off at the end to 3 significant figures. And the time, or the period, for the planet to go around the sun is 11.862 years. And now what's this going to be? Well, we're gonna figure that out here. If you take this number and you cube it and you divide by this number squared, you get 1.00. It's worth doing that on the calculator to just check that out. And then if we look at Saturn, we have 9.5388 astronomical units at a period of 29 years, 29.458. And if you take the 9.53, etc., and cube it, and take the 29 point whatever years and square it and divide, you also get 1.00. So what we could say is that the observed Kepler constant in these units is 1.00 astronomical units cubed over years squared. Now, I had a lot of fun teaching astronomy to non-science majors, and I wrote a paper on Kepler's third law without a calculator, and published it in the physics teacher. And it goes something like this. I tell the students the law is r cubed equals t squared, and that's the law in the units, astronomical units and years. And then say for the Earth, r is 1, so 1 times 1 times 1 equals 1 times 1. Everything checks out. But then we try Jupiter, and I tell them that the r is 5, and I ask what is 5 times 5? They say 25. I say, suppose you multiply by 5 again, and that's 125. Say, what number squared is close to this? And here we have 121 is equal to 11 times 11, 11 squared. So that means for Jupiter, the period is about 11 Earth years. See how close that is by an estimate? You know, we had rounded this down. We did little approximations here. Then if we go with Saturn, I'm going to make that 10, that 9.5, and 10 times 10 times 10 is 1,000, and that's roughly 900, and that's 30 times 30, and say 30 years. So that's kind of cool, play around with that. Well, let's get back now to our theory, because the theoretical calculation for K, which I derived in another class, is the gravitational constant times the mass of the sun divided by 4 pi squared. So let's put in some numbers here. So the theoretical K is, now G, we had to wait for G to be measured 7 decades after Newton passed away. It's something like, you know, like you had to wait a while. So at the time, they didn't really know what G was to any precision. And you could say, well, we could use Kepler's law in reverse and find out G, an estimate, but we're going to use the modern value for G and work with that value. So G is 6.674 times 10 to the minus 11 Newton meters squared over kilogram squared. And we're going to need to divide by 4 pi squared. And then we need the mass of the sun, 1.989 times 10 to the 30th kilograms. Now, before I go on, let me show you why G has those units. From the force of gravitation, universal gravitation, we looked at this formula in an earlier section. You know, we had, say, the mass of the sun, and we have, say, mass of a planet, and the distance between between the centers is r. And let's look at some dimensions. Now, the dimension for m, this is going to be kilograms. This m is going to be kilograms. And then this is going to be meters. Now be careful that this is mass and this is meters. And kind of to keep that straight, we might say the unit for r is m. So that's keep things straight. And the unit for the force is equal to the unit of g, unit of mass, over the unit of whatever r squared is. So now if we look at this, we can see that we have to get newtons here, n for newtons. And here we're going to have g, and then mass times mass is going to give kilograms squared. And then r squared is going to give meters squared. So you see the g has to be Newton times meter squared over kilogram squared, so that the kilogram squared cancel, the meter squared cancels since the meter's in the denominator, and you're going to get newtons remaining. So that checks out. Now, what about the units for K? The Kepler's third law constant. Well, we know that's going to be a length cubed over a time measurement squared. So let's go ahead and check that. To do that, I'm going to write down Newton, F equals ma, which is then kilogram for m, and meter per second squared. Now this, when I plug this in to there, I'm going to have kilogram times meter cubed, and this is going to be divided by kilogram squared and second squared, and then I have a kilogram coming from that one over here. Kilogram and kilogram going to cancel a kilogram squared, and I'm going to be left with a length cubed over a time measurement squared, which is what we need. The only problem is I want to get this expressed in terms of astronomical units instead of meters, and I want to get the time for unit in years rather than seconds. So this we can do by converting units. Before we do that, let's write down what our theoretical K value is by using a calculator to work all this out. And when you do that, you get 3.362 times 10 to the 18th. And then you have your meters here cubed over your second squared. So that's what it is. So we need to get rid of the meters and we need to get rid of the seconds. Well, how do we do that? Well, we know that one astronomical unit, the distance from the sun, to the earth, is 149,600,000 kilometers. So that's 1.496. Gotta go over 2 decimals and then 3 and 3. So that's 8 times 10 to the 8 kilometers. But we want meters. So a kilometer is 10 to the 3 meters. So we need to have 3 more zeros for meters. 1.496 times 10 to the 11 meters. So now we have our conversion. For the year, we have 24 hours in a day, and each hour has 3,600 seconds because there's 60 seconds in a minute and 60 minutes in an hour. So 60 times 60, 3,600, 24 hours. But for the year, we need to multiply by how many days in a year? 365 and a quarter. Remember the leap year that we need to use every 4 years. So when we do that, we'll have the seconds. So working all this out on a calculator, we get 3.156 times 10 to the 7th seconds. So now we're ready to substitute for 1m, 1 AU divided by that number. I had a chemistry teacher as a freshman that said you could always multiply a value by unity and therefore not change the problem. Then what he would suggest is set this up where you have, say, you need to cancel that meters cubed and make it AU cubed, and then put in the numbers so that that would equal a 1 and then multiply through. That's equivalent to just saying 1 meter is 1 AU divided by this and then putting in for the 1 meter what that is. So let me do it that way. So I would have here 3.362 times 10 to the 18. And now for the meter cube, we're going to put in 1 AU divided by this number. So I'm dividing both sides by this number. So I have 1 meter equals that. So doing that, I have 1 AU divided by 1.496 times 10 to the 11th power. And that's going to be cubed. See, it's a big set of numbers here. And then for the 1 over second squared, if I use this equation, I could get 1 over second by bringing the seconds over to the left side and bring the year to the other side. I would have this here divided by year. So let's go ahead and check that. If I bring the year over here, I get 1 year. And if I bring the seconds over here, I get the proper amount of seconds. So I need 1 over s, that's squared. So I need 1 over s, I'll put this in here. 3.156 times 10 to the 7th over year. And I need to square that. And that's it. Now, what am I supposed to get here? Well, since I have AU cubed over year squared, I hope that we're going to get 1, since that's the observed value, and this is the value calculated by Newton's law of motion, F equals ma, and Newton's law of universal gravitation, the force here. So let's see what we got here. If we look at these two together and very carefully with a calculator work that out, you get 2.975. I encourage you to work these out. 10 to the minus 19th, and that's going to be AU cubed over year squared. Now I'm going to come in here and grab this piece and that. Multiply this together. And when I do that, I get 1.000 AU cubed over year squared. And I'm going to go with three significant figures, 2 beyond the decimal. So that means that the theoretical calculation gives 1.00 astronomical units cubed over year squared. And that agrees to what we found earlier by using planetary data, 1.00 AU cubed over year squared. And you might consider using a spreadsheet to put in all 8 planets and let the spreadsheet work it out and see if you get this. So that's our conclusion. This is a marvelous agreement with experiment. And just to point out that later, Einstein in 1915 came up with general relativity, which is our modern theory of gravitation. And when gravitational fields get weak, when there's less mass, you find that Newton's law of gravity is recovered. And so is the F equals ma. So everything kind of works out. However, work is still being done with Einstein's general relativity because there's some problems when you work with quantum mechanics, how to bring those two together. So physics always evolving. But the neat thing about this is that in the limit, when you have weak gravitational fields, say weak gravity, you then recover Newton's universal law of gravitation. You get this. However, Einstein's work goes on and shows that black holes can exist and other things, gravitational radiation and whatnot. But anyway, that's getting a little bit beyond what we're interested in here. We're doing this classical physics, this excellent agreement. We'll see you in next class.